Hello and welcome to this chemistry video on limiting reactants or limiting reagents. And I've got my space up in honor of the Falcon 9 launch of the SpaceX craft today, May 30th, 2020, the first NASA space launch in a very long time. We're back. And this is a video on limiting reactants, back to chemistry. Chapter 3 is on stoichiometry in Brown, Burston, LeMay, and Murphy's chemistry, the central science. Let's dig in. I think they did a stupendous job of introducing the idea of a limiting reactant with the sandwich equation. I like sandwiches. And so this is a wonderful formula of a cheese sandwich. What do you need for a cheese sandwich? I personally prefer a little meat, maybe salami, maybe a little pepperoni, ham even. But let's just keep things simple. We're only in chapter 3, right? The last section of chapter 3. But we're going to make a cheese sandwich. We're going to need some bread, right? So we need 2 slices of bread, 1 slice of cheese to make a cheese sandwich. Bread to CH for cheese, right? Okay, brilliant. Okay, let's say, however, we only have 10 slices of bread and 7 slices of cheese. Now, how many sandwiches can you make with that? Okay, you can only make 5 sandwiches with this because you need 2 slices of bread for every sandwich. So we're going to make 5 sandwiches out of 10 slices of bread. That means we've got 2 extra slices of cheese. Now you could slip it into the other sandwiches, but that's not important right now. That's not the formula. And so we have 2 excess reactants, 2 slices of cheese that we're not going to use. Okay, so this is the concept of a limiting reactant or a limiting reagent. If you don't have the bread, you don't have the bread. Or if you don't have the zinc, you don't have the zinc, or whatever it is, the formula is. Whatever the smallest component, as it were. It's a little more complicated than that because sometimes you need 2 slices of bread, right? Because 7 is less than 10, but you need 2 per slice of bread. But whatever the kind of the lowest common denominator, that's the limiting reactant. Okay, let's look at these. Reagent, reactant, same thing. So the reaction is going to stop as soon as any one of the reactants is used up. No matter how much you have of the others, as soon as any one of the reactants is used up, the reaction is going to stop. Then, as we said, whatever remains is excess reactant. So we had 2 extra slices of cheese. That was excess reactant. Now, if the reaction's happening in open air, probably oxygen is going to be the excess reagent, right? Because there's plenty of air around here. Lots of air. Yeah, I'm glad I'm not on Mars. Okay, so watch the coefficients, because we needed 2 slices of bread. So you have to pay attention to the numbers in front of the various reactants and products. It's going to matter as we see as we now launch into an example. Okay, so here is an example. Let's say we have some solid zinc, and we're going to mix it with silver nitrate in solution, aqueous. What is that going to yield? Well, it's going to yield 2 silver, solid silver. Take that to the bank, plus zinc nitrate in solution, aqueous. Okay, so there's the basic reaction. Now let's say that they only give us, well, we don't know yet what the limiting reactant is, right? They give us 2 grams of zinc, and they give us 2.5 grams of solution, silver nitrate solution. Okay, so we're going to mix these. Which one? Maybe it's exactly right. Let's find out. What's the limiting reactant if there is one here? Okay, so let's find out moles. The gram doesn't mean anything. We got to figure out the moles, right? So we've got 2 grams of zinc. Now the way the book does it, Chemistry, the Central Sciences, they do 1 mole over 65.4 grams. By the way, we have 3 sig figs, so if I'm consistent, I'm going to go with 3 sig figs. All right, it got me the right answers because this is from the example box. Okay, so 2 grams of zinc is what I have. Now, zinc is the molecular weight of, the atomic weight of zinc is 65.4 grams per mole. So grams divided by grams per mole gives you moles. It's worth memorizing if you're taking a course in chemistry, right? You could do the 1 mole over 65.4 grams, fine. It's the same difference. You're going to divide this by this. So we find out that we have 0.03 moles of zinc. All right, hold that thought. How much silver nitrate do we have? Well, we have 2.5 grams of silver nitrate. Well, if you add up all of these, so oxygen is 16 times 3 is 48, nitrogen's 14, and then silver, I forget exactly what it is, but I did it in preparing this video. So 170 grams per mole. So I'm going to divide grams by grams per mole and get moles. So we have 0.0147 moles of silver nitrate. Okay, now let me go back to the original equation here. Actually, it's at the top. I don't have to. So I need 2 silvers for every 1 zinc. It looks like, well, there's no contest here. I've got way more zinc than I have silver nitrate. I need twice as much silver nitrate as I do zinc anyway. So I need even less of this. So I've got plenty of zinc. I got lots of zinc here. I don't have lots of silver nitrate. And so it's pretty clear that the silver nitrate is the limiting reactant, because I'm going to run out of silver nitrate long before I run out of zinc. Okay, so let's keep going. So the ratio of silver nitrate to silver is 1 to 1. So if I'm trying to get from here to here, well, I need 2 of these to 2 of these, so it's 2 to 2, 1 to 1. And so I don't have to do anything with the prefixes. 0.0147 mole, 3 sig figs of silver nitrate is going to yield 0.0147 moles of silver in theory, okay? So let's now figure out how many grams of silver I'm going to end up in a perfect world. So 0.0147 moles of silver times 108 grams per mole, that basically, again, 48 plus 14 plus whatever silver is, 108. And it's going to yield 1.59 grams of silver. Okay, great. The ratio to zinc nitrate, go back to the formula. Okay, so if I have this, how much of this am I going to have? Okay, the ratio is 2 to 1, so I need 2 of the silver nitrate for every 1 I'm going to get there. So if I have 0.0147 moles of this, then I'm going to end up with half as much moles, because it's 2 to 1. This is 2 times this, of zinc nitrate. Okay, well, what does that look like? Well, I take 0.00735 moles of zinc nitrate, and I multiply it by grams per mole. So the moles are going to cancel out. I'm going to get grams. I did mess up on the sig figs here. Oops. It came out right anyway. It should have just been 189 because 3 sig figs. 1.39 grams of zinc nitrate. All right. Happy days are here again. Now, what about that excess reactant, excess reagent? So if I go way back, the relationship between silver nitrate and zinc is 2 to 1, right? If I have 0.0147 moles of silver nitrate as the limiting amount, then I'm only going to use up half that much of zinc, 0.00735 moles of zinc. So let's multiply moles by grams per mole. The moles will cancel out. This is, again, the molecular weight of silver nitrate. And basically, I'm going to only use 0.481 grams of zinc. Well, how much did I have? I started with 2 grams. So I'm going to basically have 1.52 grams of zinc left over. I can take that to the bank too. Okay, so you get the concept that a lot of times in a reaction, you have an overabundance of one reactant. The one that you don't have an overabundance of is the limiting reactant or the limiting reagent, and that's going to determine how much of the reaction is going to actually take place, and whatever's left over is the excess reactant. Okay, the second concept in this last section of the chapter is theoretical yield. I don't know if you were listening, but I mentioned that we don't often get a perfect result. We usually get some sort of a percentage of what we theoretically should have gotten. And so the percent yield is basically the actual amount we get divided by the theoretical amount we should have gotten times 100. I wish somebody had told me this when I was in chemistry, because I was very, very, what's wrong? I'm not getting everything. Anyway, there was actually one time where I got more than I started off with. That's not real. That doesn't happen. Anyway, the reason why we don't get necessarily the whole theoretical yield, perhaps only part of the reactants react, or maybe you have side reactions that siphon off some of the materials, or maybe you may not just not be able to recover 100% of the yield. So we talk about theoretical yield as what we should have in theory gotten, actual yield as what we actually got, and then percent yield is basically the actual divided by the theoretical times 100. Okay, so let me do another example from this section. So let's say we've got iron oxide plus carbon monoxide is going to react. This is in solid, this is in gas. It's going to react to get iron plus carbon dioxide, okay, in gas form. All right, so let's say that we have 150 grams of iron oxide here, okay? So that's the limiting, we're told that's the limiting reagent. Okay, so I add up all this stuff here, and it's the molecular weight of iron oxide is 160 grams per mole. Grams divided by grams per mole is going to give me moles. So basically I have, in this reaction, I'm told 0.938 moles of iron oxide. Okay, so the ratio between, what are we doing? We're going to iron, from iron oxide to iron. The ratio is 1 to 2, right? 1 in front of that, 2 in front of that. So basically, if I multiply this by 2, I'm going to end up with 1.88 moles of iron. I had this much moles of iron oxide, but I'm going to get twice as much moles of iron. Okay, 1.88 moles of iron. So now let me get back out into grams. So moles times grams per moles, moles cancel out, I get grams. So the atomic weight of iron is 55.8 grams per mole. Paying attention to sig figs here, 3 sig figs. Okay, so multiply it out, and I should have ended up with 105 grams of iron, theoretical yield. That's what it should have ended up. But then I'm told that I didn't end up with 105 grams of iron. I ended up with 87.9 grams. What's going on here? There's no justice in the world. And so basically, there should have been a division here. So I'm sorry, I made a mistake. Let me correct it. I can correct it. Phew, there we go. So if I divide the actual yield by the theoretical yield and multiply it by 100, ta-da, we had an 83.7% yield, percentage yield. Sorry, it's not a perfect world. Well, this has been a video on limiting reactant on the day that we went back, NASA went back into space, May 30th, 2020. Have a great day.